Okay, welcome everybody to this morning session. The first speaker of the session will be Mikhail Shaposhnikov. He will tell us about conformal symmetry towards the link between the Fermi and the Planck scale.
Good morning, everybody. It's a pity we cannot meet this time, so this is all remote. Anyway, what I'm going to talk about is a possible link between the Fermi and Planck scale, which may be related to conformal symmetry. What I'm going to tell you about is based on several works with my collaborators, Andrei Stern and Sebastian Zell, and the references to the relevant papers are this page. There is a paper this year and a couple of papers during last 2 or 3 years or so. Okay, so I'm going to start from motivation, and I will describe my view on naturalness, and then I will turn to the question of possible non-perturbative semi-classical relation between the Fermi and Planck scale. Okay, so naturalness. What is naturalness? Okay, I mean, as usual, you can go to Google and check the meaning of all possible words. And what one of the dictionaries will tell you that if you say natural, this means that we are talking about something which has existed or formed by nature based on state of things of nature, relating nature or the universe, etc. If we try to Google what natural means, you will find out that this is contrary to the laws of nature, at variance with what is normal or to be expected. So in common language, and I would prefer to use common language here, natural is something which exists or formed by nature or based on the state of things of nature, constituted by nature, whereas the natural is something which is contrary to the laws, of course, of nature. Now we can come to particle physics. And what we find there, that the standard model is complete now. The last particle, Higgs boson, predicted by the standard model has been found. No significant deviations from the standard model have been observed. And with experimental values of masses of top quark and the Higgs boson, the standard model is a consistent effective field theory all the way up to the quantum gravity scale. In spite of this success, the standard model is called unnatural, whereas the theories with low energy supersymmetry, composite Higgs boson or large extra dimensions are profiting from being called natural. I would say that this looks to be unfair to a natural standard model, since it describes the nature better than the natural theories. Okay, on more serious grounds, the notion of naturalness in high energy theory is a rather technical criteria. So it can be formulated in the following way. Physics at the electroweak scale, or right above it, should be organized in such a way that quadratic divergences in the Higgs boson mass are eliminated to remove sensitivity of the Higgs mass to physics at very high energy scale, for instance, grand unified scale. And if this doesn't happen, the theory is called unnatural and fine-tuned. And normally, this is represented in the following way. You consider different quantum corrections to the Higgs mass. There are standard model loops, in particular, the loop of top quark, and there is some kind of new physics contributions. So all these guys are divergent quadratically, but there is consideration with the first contribution and the second contribution, and this look to call, so this ideology, this way of thinking, it calls for new physics right above the electroweak scale. Okay, if you go back to history, so I would say that the first time the hierarchy problem or problem of naturalist appeared quite a while ago, back in 1976, with the paper by Eldar Gilman. And all this consideration, it was based on grand unified theories of strong, weak electromagnetic interactions. So at that time, well, a little bit earlier, grand unified theories of these interactions were invented, and these theories, for the first time, showed the possible existence of very heavy particles left to work with the mass greater than 10 to the 15 GeV. So this very large mass, it was required by gauge coupling unification, and it was also needed from a phenomenological point of view, as only in this case the proton is sufficiently stable. So this leads us to two different theories with two different scales. So one scale is scale of grand unification, another scale is the electroweak scale, and the ratio of these two scales is a very large number, 10 to the 28. So first, what that would mean? That would mean that we need some ad hoc fine-tuning between parameters, masses of couplings of different particles at the tree level with the accuracy of about 26 orders of magnitude. But moreover, what Bill Benner has noticed is that even if you make this fine-tuning at the tree approximation, then you will have to repeat this fine-tuning many, many times in order to compensate contributions coming from one loop diagrams, two loop diagrams, etc., etc. And that you should do well, many times up to 14th order of perturbation. Okay, and so this led to a conjecture, to a requirement of naturalness, requirement of absence of quadratic divergences in the Higgs mass in order to avoid these fine-tunings. And there were different proposals to cure this problem. One of them is associated with low energy supersymmetry. When you get compensation of bosonic loops by fermionic loops, two other directions are associated with composite Higgs boson, new strong interactions, or large extra dimensions. All of these proposals require new physics right above the Fermi scale, which was expected to show up first at lab, then at LHC, but this didn't happen. And I would think that it's time to think about change of paradigm, okay? So in all this discussion, the source of hierarchy problem are heavy particles, at least in quantum field theory, okay? And these are heavy particles with substantial coupling to the Higgs boson. So if there are no heavy particles, say no grand unification, then we don't have large perturbative contributions to the Higgs mass, and therefore we don't have fine-tuning. So for instance, the standalone standard model, if you treat it in perturbation theory, forget about Landau pole, then this is the theory with just one energy scale, and there is no hierarchy problem, there is no fine-tuning problem there. So I would think, and this is a proposal, that the naturalist criterion can be replaced by another one. So I would say that instead of saying that the physics right above the Fermi scale should be organized in such a way that there are no quadratic divergences in the Higgs mass, I would say that UV physics, gravity in particular, should be organized in such a way that Fermi scale is much smaller than the Planck scale. Okay, so Planck scale is, of course, there. This is the scale of gravity. I would like to stress, though, that the Planck scale itself is not a mass of any particle. So it's not a mass which runs in any type of the loops, but this is the strain of interaction. So if we try to explain this large difference between the Planck scale and the electroweak scale, you may think about non-perturbative effects, because non-perturbative effects are the effects in which we can get in a natural way, as a result of computation, a big difference between different scales. So some of these effects are related to tunneling. So for instance, the theory of alpha decay, in which some heavy nuclei decays into alpha particle plus less heavier nuclei. So this is a tunneling process. Yet another example is the tunneling. The simplest example is double well potential, where the splitting between energy levels is much, much smaller than the energy level itself. But that's tunneling is not a unique place where exponentially small numbers appears. Yet another example is mass gap on BCS superconductor, where the critical temperature is exponentially suppressed in comparison with the device screening layer. Okay, so it may be very well that there is just one fundamental scale in nature, the Planck mass, and the electroweak scale is generated from its non-perturbative. And if that's true, the huge difference between the Higgs mass and the Planck mass can be associated with non-perturbative phenomena in gravity. And if we talk about semi-classical physics, then the Higgs mass may be related to the Planck scale as like this. So we have some exponential suppression, and the exponential there is about 80. 80, of course, is an empirical number. Okay, so can this picture work from phenomenological point of view? So if there are no new heavy particles, such as lepton quarks, super heavy right-handed neutrinos, supersymmetry, we can ask ourselves what explains the origin of neutrino masses, the dark matter, baryon asymmetry of the universe, cosmological inflation. So these are all the manifestations of physics beyond the standard model. Okay, so the answer to this challenge can be pretty much simple. And all these problems can be resolved by relatively light but feebly interacting particles with mass below the Fermi scale. And the concrete example here is nu MSM, in which there are three new particles, right-handed neutrinos, which are complementing the left-right symmetric structure of the standard model. In this theory, all the particles have masses below the Fermi scale, and you can get a simultaneous solution of all the phenomenological problems which I described above. Okay, now let's come back to more theoretical issues, and let's see what kind of requirements the theory which can allow this exponentially small corrections to the Planck scale manifesting itself as the electroweak symmetry breaking scale. Okay. So first of all, we should have a theory in which mass of the Higgs boson is equal to zero perturbatively in all orders of perturbation theory. Because if this is not the case, then perturbative corrections will dominate exponentially suppress non-perturbative corrections, and the scalar Higgs mass can be driven up to the Planck scale. Another requirement is the absence of super heavy particles strongly coupled to the Higgs boson. Okay, because if these particles appear, again they will contribute in the loop, so we will get large corrections to the Higgs mass. Yet another requirement is existence of semi-classical configurations which would lead to non-zero vacuum expectation value of the scalar. Okay, so let's look at the first requirement. Do we have any symmetry protection which leads to zero Higgs mass? So if we put the Higgs boson mass to 0 in the standard model, then the classical Lagrangian of the standard model has a slight symmetry. It is scale and even conformally invariant. So to remind you, derivations are global scale transformations which change the scale of the field and the scale of coordinate. And sigma is the canonical dimension of the corresponding field. So classically scale invariant conformal theory, they have many attractive features. They don't have any explicit mass parameters, only dimensionless couplings. And we can consider them as a playground in which the breaking of the electroweak symmetry and generation of the Higgs mass comes through quantum physics. And the very first example how this might happen showed up already many years ago, okay, in very well-known Coleman and Weinberg paper. Okay, so the logic there was, let's take a theory which is scale invariant on the classical level. Okay, abelian Higgs model was an example. And what Coleman and Weinberg showed that in this theory, essentially due to the breaking of scaling symmetry due to quantum corrections, this theory leads to the Higgs phenomenon, the scalar mass is generated, vector mass is generated, and moreover, there is a fixed relationship between the mass of the scalar boson and mass of the vector boson, and the ratio of the two is expressed through the dimensionless couplings of this theory. So how does it happen? It happens because the scale invariance is anomalous, there is dimensional transmutation, the renormalization group programming of parameters leads to non-vanishing contribution to stress energy tensor. The physical quantities depend on renormalization scale only logarithmically. This is most easily can be seen in dimensional regularization. We can look at a renormalization group equation for the parameter which would be the Higgs mass, and the main point here is that scale derivative of the Higgs mass is proportional to the Higgs mass itself, meaning that mass of the Higgs equal to 0 corresponds to the fixed point. This means that there is no counter term needed for this renormalization, and this leads to the possibility of prediction of the scalar mass. Okay, so this idea at the time was extremely attractive, and many people invented theories which in which the electroweak symmetry breaking occurs in this way. Okay, there was a prediction of the Higgs mass at the time, so that mass of the Higgs should be below 10 GeV, but all that was rejected by experiment. So the situation is sorry. So the situation is that if the top work mass is smaller than the critical value, then the minimum of the effective potential is generated at a very small energy scale. About 100 mega electron volts due to the chiral symmetry breaking in QCD. Now, if the top work mass is larger than some critical value, then the extra minimum of the effective potential is generated at the Higgs vacuum expectation values, which is much greater than the Planck scale due to the top work loops. And amazingly, this critical value is somewhere between 170, 174 GeV, accounting to uncertainties in the relationship between the Monte Carlo mass, top mass, and all mass of the top. Okay? So whatever the mass of the top quark is, if it's in this region, then we get either a very small vacuum expectation value for the Higgs group or very large. And so both possibilities are not good. They are rejected by experiment. Now, of course, you can try to correct this situation and save the idea by extending the standard model, introducing different new particles, new fermions, new gauge groups, etc., etc. However, the whole strategy here is somewhat flawed by the following argument. So we know that there is gravity, okay? So, and gravity comes with dimensional full parameter, the Planck scale. And if we have explicit Planck scale in the problem, this means that the conformal symmetry is broken by the gravitational effects. And since the Planck scale is very, very large, then the question arises whether the presence of gravity in the standard model, gravity plus the standard model, doesn't change this picture. Okay? So this picture is not changed from the perturbative point of view. Why so? Again, take mass independent regularization, such as dimensional regularization. In this regularization, all infinities or all divergences, all counter terms, they are polynomials with respect to coupling constant. The gravity induces coupling constant, which is inversely proportional to the Planck scale. And so all the corrections to RG evolution here remain suppressed by the Planck scale, and the existence of the fixed point, MH equal to 0, remains true. Okay, so if you have standard model plus gravity, we believe that conformal symmetry is broken only very weakly, then we still can predict the Higgs mass in this. Okay, so the graphics conformal standard invariant standard model is an ideal playground for looking for non-perturbative generation of the Planck scale. Okay, so with that in mind, we can look for the simplest theory, which may realize this idea. Okay, and the simplest theory, which happened to be quite simple by itself. So we can consider a scalar field with a non-minimal coupling to Palatini gravity. Okay, it will be clear after some time why Palatini gravity is a good candidate here. Okay, so the basic structures in Palatini gravity are distances and symmetric connection. The action of the scalar field plus Palatini gravity is written here. I allow for non-minimal coupling of the scalar field to R, and then we have a scale invariant, conformal invariant potential for the scalar field. Okay. So the dynamical variables in this theory are connections and the metric. Variation with respect to connection gives requirement of metricity, relationship between gamma and G. The variation with respect to G gives Einstein equation. And in fact, what happens in this theory, that if non-minimal coupling is present, then the large parameter psi happens to be a semi-classical parameter, which would allow for non-perturbative estimate in Palatini gravity. And the metric gravity, so the same type of Lagrangian, but gamma is not an independent variable, doesn't provide such a semi-classical parameter. Okay, so this field phi, I will call it the Higgs field. So this theory is not defined at all energy scales. It has a cutoff, so at which interactions in the scalar sector become to be strong, and this scale is not as high as in Planck. So in Planck would be a cutoff of the gravity theory, but for scalar theory, this cutoff is m Planck over square root of psi at energy larger than that value. We will get the perturbation theory explodes. Okay, so what we want to find out, we want to compute the Higgs vacuum expectation value, and I imagine that this can be done writing down the path integral where you integrate over all degrees of freedom, including gravitational degrees of freedom. Okay, so semi-classical approximation leading to exponentially suppressed contributions is better formulated in Euclidean space-time, and that's what I will be doing here. There is, of course, a caveat that Euclidean path integral is not well defined due to the problem with conformal factor of the metric. So one can imagine that eventually the Euclidean quantum gravity result can be derived from Minkowski path integral by doing some non-trivial analytic integration. So I'm going to ignore this problem and follow other people work. Some of the names are written here who were using Euclidean path integral for gravity. Okay, so we want to estimate this path integral. If we consider scalar fields which are much smaller than the Planck scale, then the gravity is irrelevant. We can compute different loops in lambda phi to the 4 theory. And as I was arguing, these loops do not produce any contributions. Okay. So the challenge which we are facing is to account for contributions where the scalar field is much greater than the Planck scale. So let's look at this theory at large values of the scalar field. So if scalar field is large, then the m Planck can be ignored, and what we are getting a scale invariant action. And this action first is scale invariant. And also, the Planck mass there is dynamical. Okay, so the Planck mass depends on the scalar field.
You just had 30 minutes now.
Mm-hmm. Okay. Yeah, I'm at the end. So let's try the following. When we can have a large scale of fields, we can go from the Jordan frame, that's the name of the frame in which the Planck scale is dynamical, to the Einstein frame, okay? So we make this transition, define the saddle point, and then we can verify a posteriori whether our computation was self-consistent. And that's what I'm going to do. So the transition to the Einstein frame is consistent in changing the metric with conformal factor omega, and also moving from to the variables in which the Higgs field has a canonical kinetic charge. Okay, so once this is done, the action looks as follows. There is the normal Einstein gravity. Then there is kinetic term for the scalar field and some potential, which is flat at large values of the Higgs field. What is most important in this transformation is that you see that here the dependence of phi on a new field phi is exponential. And this means that for large values of the Higgs phi, when we make this transformation, this phi field, and we want to find out the average of this field, it depends exponentially on the field phi. So this guy appears in exponential, and in order to find the saddle points of this path integral, we have to minimize not just this action here, but the action plus this extra source term. Okay, and this leads to modification of the action and equations of motion, and that leads to existence of new solutions which minimize the action. Okay, so this type of thing is pretty much similar to computation of this integral by the saddle point for large n. Okay, so if you just take the saddle point x equal to 0, your result for large n will be wrong, so you will have to write your logarithm. And there are other examples in more physical situations, like computation of multi-particle production or proof of confinement in three-dimensional geologic glacial mode. Okay, so after this is all said, everything else is straightforward. Okay, so you can write down field equations in the Einstein frame for maximally four symmetric metric. So I write here the expression for this metric. So you write down equations of motion, and this is a new source term, which is actually singular. You can find the solution, and the most important point here is the existence of semi-classical expansion parameter. So you can write what the action is in spherically symmetric configurations. You can make different rescalings and show up that the classical action is indeed proportional to square root of psi, which is an analog in 1 over h bar in quantum mechanical semi-classical approximation. Okay, so taken at the face value, the action actually the program fails. Okay, the program fails because this singularity, delta function singularity, which appears here, is too strong, and you get an infinite action. But it would be too naive to think that this is just the final action, and one can modify the action by adding a higher dimensional operator. Okay, and these higher dimensional operators will, in general, regularize the corresponding singularities. Okay, so if we say that we don't want to introduce new degrees of freedom, and we don't want to scale asymptotic scale invariance when scale of field is equal to 0, we get many different operators which satisfy this requirement. And this is an example of operator which satisfies the requirement that there are no new degrees of freedom, and it doesn't spoil asymptotic scale invariance, and it regularizes the infinities. Okay, and also this operator is successful from the point of view of the action for this configuration. Okay, so if this picture shows that this axis here is our semi-classical parameter. This is psi, logarithm of psi, and this action here is the ratio of the parameter delta, which stands here, and this semi-classical parameter psi. Okay, so if you take delta of the order of psi square, then the cutoff, the appearance of strong interactions coming from this new term is the same as in other sectors of the theory in Planck over square root of psi. Okay, and along this line, we just get the action 80. Okay, so this is not a prediction. We don't know what delta is, what psi is. Here, the purpose is to see whether a reasonable choice of these parameters can lead to the hierarchy. Okay, so along this line, we get the hierarchy. It's interesting that exactly the same theory can be used in completely different domain of physics. This theory can be used for inflation, and then within this square, okay, the inflation is successful, and okay, so here there is some upper limit coming from phenomenology, again, top quark mass. What is the top quark mass from experimental measurements, and whether accepted inflation is successful or not in this theory. Okay, so I would conclude from here that hierarchy between the Planck and Fermi scale may be a natural phenomenon if the standard model is classically conformal, psi is large, and the gravity is of Volatility type. Okay, so that doesn't say that this is the only and unique solution. There could be other solutions. Okay, other forms of this operator may even not lead to the required action. Okay, so other completion of the standard model at very high energies doesn't have this property. Okay, so in other completions, the mass of the Higgs generated in this way would be of the order of the Planck scale. But here, what is important is the existence proof. And so let me just conclude. So I would say that the standard model now is in the great shape, and perhaps its success is telling us that there is no new physics between the Fermi and Planck scale. We would get to the hierarchy. That new physics is hiding below the Fermi scale. And the reason why the Fermi scale is much smaller than the Planck scale is rooted in conformal symmetry and non-perturbative. Thank you very much for your attention.
Okay. Thank you very much for this very interesting talk. So now I will open the floor for questions. I can see Irina has her hand up. Irina, please go ahead.
Okay, thank you for a very interesting talk. I have the following questions. In your consideration, conformal symmetry plays an important role. What happens if you deal instead of conformal symmetry, superconformal one? Do we can expect some profit from such type of consideration? Thank you.
Thank you, Ira. I don't know. The answer is I don't know. I didn't think about that.
Okay.
So, no.
Do you think it is reasonable to start with consideration or something like that? Because supersymmetry is more close to strings and so on. To superstrings, I mean.
You see, my problem here is the following. If you talk about superconformal symmetry, that would imply supersymmetry, right? And that
Exactly.
would
exactly.
And that would imply supersymmetric particles. So if I come to supersymmetric particles, and if I stick to kind of standard thinking about naturalness, then these particles should be at the electroweak scale, and they were not found there. And that make me think that maybe supersymmetry is there, but not at electroweak scale, much higher. And, but if it is much higher, then there are heavy particles which are going to contribute to the mass of the Higgs, and then we are again in trouble. So.
Valerie?
Yes. Misha, can you also calculate the effective potential, not just the vacuum expectation value of the Higgs field?
The short answer is I don't know how to do that. Okay, so that's very good questions, but we were not able to provide any reasonable formalism, so we didn't figure out how to do that. But yeah, I would be. Yeah, that's.
Arkady?
I don't know. Okay, so it would be a great thing to do. I don't know how to do that.
Hi, Misha. It's I'm trying to mention that I believe that it was very old paper by Bill Bardeen. You know, I don't know if you're aware of his paper, where he kind of propagated this idea about kind of absence of quadratic divergences, implying that it is kind of conformal behavior of the theory, and essentially he was talking about perturbative regime. I mean, not about, you know, so it's not about your kind of non-perturbative connection between Planck scale. And in this sense, I'm trying to check whether my understanding of what you are saying is consistent with this, that in perturbation theory, you have this kind of inhomogeneous term in you know, group equation, right? That d over mu d over d mu over mh square would be not just proportional mh square, right? If you count in standard, you know, kind of quadratic divergences, right?
Yeah.
Right, okay, but he argued, I mean, Bardeen argued that that in this way, at the level of quadratic divergences, even if you are not making theory, you know, kind of conformal, you know, you discuss this particular conformal variant of the theory, that at the level of quadratic divergence, you can say, I don't know, that it's still that they are not there. That there is no quadratic divergences of the theory, classically conformal, and the quantum level, if there is breaking of conformal values, it's not at the quadratic level. Okay.
Yes.
So the whole story of say, when you are saying that there is this fine tuning, for example, that fine tuning implies, I can understand that if you believe that, say, series regulated or converged at a Planck scale or whatever, then I understand what about fine tuning. But if it's kind of just perturbation theory, my impression was that you are saying essentially close to this, that then you can fix the Higgs mass, and the notion of fine tuning maybe not having much sense. Does it agree with you what you are saying?
Yeah. Yes, Arkady. Of course, I do know about Bill Bardeen paper, and I share this thing which he said here. Yes.
I see. Okay. Thank you.
No, I mean, the short answer, yes, I'm with him at this point. Well, I didn't put his name. I forgot, but yes.
Okay. Thank you, Mr.
Okay. Any last minute question? Anybody else? Okay. Let's thank Mikhail again.